Hello, welcome to lecture number 1 for the course Physics 303A. If you recall, this course deals with applications, principles of lasers and their applications. So I'm going to focus basically on laser applications. To begin with, the first application which I want to talk about today is going to be laser cooling. Now, as you know, lasers are usually known as entities used for either having immense power or brightness, which are used for cutting, melting, and variety of such processes that involve breakdown of material. On the other hand, lasers can also be used to get the lowest possible temperatures in the universe. So, for example, with lasers and a collection of atoms, you can cool the collection of atoms to about microkelvin by using purely lasers. And you can even go lower by employing something called evaporative cooling and so on. And one can get to temperatures as small as nanokelvin. So we are not, of course, going to go all that far. We are going to look at the first few steps towards laser cooling. And what I want to focus today or in this course is largely Doppler cooling. All right. So you know the Doppler effect, and one is going to use that Doppler effect to essentially cool atoms. So with Doppler cooling, typically one can get to temperatures of the orders of hundreds of microkelvin. There is another mechanism for cooling. It is called the polarization gradient cooling or Sisyphus cooling popularly, wherein one can actually go about 2 orders of magnitude lower and one can get to about microkelvin. To go below this temperature, one would need to employ other methods like evaporative cooling and so on, which I will not get into. I will also not go into Sisyphus cooling as it requires some understanding of internal atomic dynamics. All right, so let us begin with this business of Doppler cooling. And what I'm going to do is I'm going to go back and refer to what we have learned. So if you recall, um, there is essentially what we are going to deal with or utilize is light matter interaction, right? So there are obviously two aspects to it. If you recall, we characterize something called a refractive index, which sort of governs the interaction of light with the atom. And this refractive index can be considered as a complex number where the real part deals with dispersive properties, whereas the imaginary part deals with absorptive or dissipative properties. So let us just look at that quickly again. So if I plot my response, if I plot my response as a function of frequency, right? So I'm plotting frequency and I'm looking at atomic response. So there is in the atom, so I come in with light, which has got a frequency h bar, which has energy h bar omega, and there is a atomic energy difference. The ground state I denote by 1. We get back to our same notation as earlier, and the excited state is 2. So you see there is a corresponding energy associated with the atom, which is h bar omega to 1, which is E2 minus E1. And there is an energy associated with the photon, which is h bar omega. And you see that if omega equals to omega to 1, right, then we have something called a resonant condition and we have maximum absorption. Okay, so let me now color code this. So absorption I'm drawing with red. So you see that this is how my absorptive response will effectively look like, right? Where the peak happens to be at the location omega 1, 2, in my frequency space. Property, that is, I am looking at, so this, again, let me emphasize, this is related to the imaginary part of the refractive index. Now let's look at the other aspect, which is the dispersive part or reactive part, where what you have is the real part of the refractive index, and you see that has got this feature uh, which looks like so, right? And you see that the refractive index exactly at resonance happens to be precisely 1, and then it has got this feature, and you can clearly see that refractive index becomes important essentially away from this resonant region. Remember, if you recall, we had discussed about the anomalous dispersion and normal dispersion. So away from resonance, what you get is normal dispersion, and within the resonant, within this region, what you get is anomalous dispersion, wherein the slope of the refractive index is different. And you see that this part is essentially what the real part of refractive index is. So you see, we have got to use both of these aspects, both of these kind of aspects, to actually affect the external degrees of freedom of the atom. Okay, so now let's step back and understand, what do you mean by Rayleigh temperature? So if I'm looking at a collection of atoms and I'm asking what is temperature, so what is temperature is essentially what the temperature is a measure of the random kinetic energy associated with this collection of atoms, right? So one is talking about one is not talking about the average kinetic energy. What one is talking about is actually the variation in the kinetic energy, or there is a distribution of kinetic energy, and that is the measure of temperature. So if I want to cool down something, what I need to do is basically lower the distribution of the kinetic energy of the atoms. I'll get back to this again, what I mean by lowering that distribution and so on. So effectively, what we want is that every atom in my collection should now experience a small amount of kinetic energy on an average, so that it goes from large kinetic energy to small kinetic energy, is giving, so that one can associate a lower temperature. All right. So what we want to manipulate is basically use the internal degrees of freedom, that is, use absorption, dispersive properties, absorptive properties, to affect the external degrees of freedom. So what do you mean by external degree of freedom? It is basically the one is applying is some sort of a radiation pressure. This might be a familiar quantity to you. Uh, you might have heard it in school. There's radiation pressure, which is basically largely involves absorptive dynamics. Gradient force, or the dipole force, if you like, and this is related to the reactive or the dispersive property of the so I'm going to represent the atom now. So what I'm going to I'm looking at the atom as representing the two internal levels of the atom, the ground state and the excited state, as 1 and 2. And then I am looking at the photon, which is light, represented this way, is coming with an energy h bar omega L standing for the frequency of the laser, and it has got an amplitude, let us call it EL, which is a vector. And for the atom, there is a small subtlety. The subtlety is that my excited state has got a finite lifetime. Like, it is not just merely a level, but I'm giving it a finite width, and this finite width, or the the width of the energy, if you like, is given by h cross times gamma. So this gamma, so where does the gamma originate? For example, if you look at spontaneous emission for a atom which is absolutely isolated, it's stationary in space, it would still have an intrinsic decay of the excited state, and that decay rate gamma would be essentially the decay coming out of the spontaneous emission rate, and that is essentially what it would be. But then there are other mechanisms of broadening, as we looked at in the laser course earlier. So let us not get into too much of that. But essentially, what we have the most basic property that governs this the width of the excited state is basically, let us take it as spontaneous emission. And apart from that, the atom itself has got a dipole moment. Atom itself has got a dipole moment, which is written as d12. It's a dipole moment, as you know, is a vector, and d12 actually gives me the dipole moment with, associated with the atom due to the transitions between the levels 1 and 2. That's coming from a quantum mechanical origin. If you look at that exact number, and what happens is, now how well does the light interact with the atom depends basically on two parameters. So one is the coupling of the dipole moment to the electric field of the light. This gives rise to something called Rabi frequency. Okay. The second parameter is basically your energy conservation, which tells me that how well does omega L match with the atomic energy difference. So let me get back to that, omega 1, 2, right? So, and this quantity, I'm calling it as detuning. So delta. So you see, these two parameters basically govern the kind of interaction the light has with the atom. So I want to represent this, let me write it down. Detuning, essentially the photon, which is not necessarily energetically matching with that of the atom. So you see that there is a difference between the energy associated with the atom and energy associated with the photon, and this quantity, actually I have represented minus delta, is minus delta, because I have called detuning as omega L minus omega 1, 2. So you can clearly see, let's get back to our previous graph. You can clearly see that this the response, the imaginary part, is largely dominant around delta equal to 0. That is when the atomic resonance omega 1, 2 matches with the field omega. Whereas the delta not equal to 0, that is the region which is away from it, is where the dispersive response comes in. Okay, so so let's look at these two scenarios. Delta equal to 0 refers to absorption, and what you have is the absorbed light is basically scattered because of spontaneous emission in all directions, right? And this aspect is related, as I told you, to the imaginary part of the refractive index. When delta is, I should be very clear, when delta is largely greater than gamma away, right, because of the width of that resonance. So let me again go back here. Let me put in a width of this thing, which I'm calling it as capital gamma. That's precisely what I represented by giving a width to the excited state. So when my detuning is larger than gamma, what I basically get is what is changing is basically the speed of light within the collection of atoms. So effectively, there is the speed of light gets modified, And this aspect is related to the real part of the refractive index. All right. So let us get back to the Doppler cooling idea itself. So let me first just convey the whole business is to now use these internal degrees of freedom like absorption and re-emission and so on to affect the external degree, which is the momentum carried by the atom as a whole, right? So let me be a little pictorial. Okay, so imagine that my atom was in the ground state. So I'm representing the ground state or the cold sort of atom in the ground state by blue. And then I'm coming in with light. This is prior to collision. And remember, the light not only is coming with an energy h cross omega L, it is also carrying a momentum, which is h cross k in a particular direction, or h by lambda, or in other words, it's h nu by. So this is prior to collision. After collision, after the interaction, the atom goes to the excited state. So I'm now representing the excited atom in that direction. But something else has happened. So atom not only took away the energy and hence went from the ground state to the excited state, it also now needs to conserve, because imagine the atom was initially stationary, it also needs to conserve the momentum. So what you're going to get is that the atom basically gets a kick, okay, where it gets a, imagine that it was initially at rest, it would basically get kick in the direction of the incoming photon in a definite direction, okay, because both the energy as well as the momentum, linear momentum, and also angular momentum, which I will not talk about here, it needs to be conserved. Okay, by the way, the angular momentum is conserved because of the internal degrees of freedom and the kind of selection rules that govern the light atom interaction. So this is what happens when I am looking at the absorption process. Now let's look at the reverse. Atom in the excited state. This is prior to the atom giving up its energy, right? And after the spontaneous emission process, the atom comes down to the ground state. Not just that, it gives away the photon in some random direction. So the photon not only takes away the energy omega L, it also carries with it the momentum h bar k in a direction. So once you have the photon taking away the momentum in that direction, obviously if the atom was originally stationary, it would get a kick in the opposite direction. So let me, which is again given by the momentum carried by the atom, where v is the velocity of the atom because of the recoil which it got because of the photon leaving it. So you see, this is precisely what is happening in the process of absorption, and this is what is happening in the process of spontaneous emission. So there you go. So you have, so now you can clearly see that now let's look at, if you want to look at the internal degrees of freedom, remember that here the electron was in the ground state before absorption. At the end of the process, the electron is in the excited state. It has gone from ground state to the excited state. Whereas in this situation, the electron was in the excited state to begin with, went from the ground state, electron came down to the ground state, and the photon is released, right? So this is essentially essentially the summary of what is happening. So the internal degrees of freedom are actually affecting the external degrees of freedom of the atom. Now let's look at, is this recoil velocity, right? V recoil. How effective is it? Is it really a large number, or we are talking about what are the kind of numbers we are dealing with? And then now my V recoil is essentially, I can write it down as h times nu, okay, m being the mass of the atom, nu is the frequency of light, and and c being the velocity of light, right? This is my v recoil. I have basically equated the momentum carried by the photon to the momentum taken away by the atom, which in our case is simply m times v. And this v is what I'm calling as v recoil. So let's estimate this number. So we are good at estimating. So this is about 10 to the power minus 34. I'm looking at all in SI units. So joule second, you have got frequencies of the order of 10 to the power of 14, right? 13, 14, depending optical. And then you have the mass, which is of the 10 to the power minus 27 kgs. And you have light velocity, free space, roughly about 10 to the power of 8. So you see that if I'm putting all these numbers together, what I get is essentially something of the order of either 10 to the power minus 1 or 10 to the power minus 2 meters per second. So that's the kind of velocity one is talking about. So if you put in the real numbers, the exact numbers, for example, sodium atom, okay, then this recoil velocity, so this V recoil for sodium atom comes out to be of the order of 3 centimeters per second. Whereas if I'm looking at cesium atoms, these are all, by the way, the alkali atoms in the group 1. Remember, we look at hydrogenic systems to make our life simpler. So the cesium atom, the V recoil, gives you of the order of about 3 millimeters per second. So it is substantial. Now we are looking at a single photon giving rise to, resulting in such a recoil velocity. Now one is asking whether this is good enough to actually cool. So now just imagine, so let's look at the accelerations. That would tell you how the velocities can change or how I can lower the temperature. So let's look at acceleration. So typically you see that the excited state lifetime, right? Remember that is related to essentially our gamma. This is order of about 10 to the power minus 8 of a second. What that tells you is that in 1 second, I would basically make about 10 to the power of 8 absorption, emission cycles, right? If I count these, I'll get about 100 million cycles in a second. That is what this excited state lifetime tells me. So the atom gets excited, emits a photon spontaneously, comes back, again does this process, and roughly that is about 100 million times. Then we are looking at a V recoil at every instance. Every absorption gives you a V recoil about, again, my apologies, it gives you a V recoil about 10 to the power minus 2 meters per second. That tells me that my deceleration, if you like, okay, it's going to be what? It's about 10 to the power minus 2 times 10 to the power of 8. Okay, that gives me roughly about 10 to the power of 6 meters per second square. Right? So imagine that is the kind of acceleration that one is able to generate by these processes. We are talking about acceleration that is 10 to the power of 5 times gravity. That's huge. What it means is that initially, let's say if my initial velocity of the atom was about 1 kilometer per second. Imagine it's coming out of an oven, which is about 400 degree Kelvin, 300, 400 degree Kelvin, and it's coming that way. So roughly in a length, which is going to be about V square, V initial square by twice the acceleration, right? This will roughly give me, so this is, we are talking about 10 to the power of 6, we are talking about kilometers, so 10 to the power of 6 divided by 2 into 10 to the power of 6, that roughly gives me about 0.5 meters. So you see, within half a meter, if this is the kind of deceleration the atom can experience, I can basically make an atom coming extremely fast to a complete stop, right? But of course, it is not all win situation, because you see that every absorption also is followed by a spontaneous emission, which gives you a random kick. That is, I can arrange in my original problem. So I can arrange my light to come in from a particular direction, right? So that would basically give definite kicks in a particular direction, absorption, whereas spontaneous emission will actually lead to randomized motion of my atom. So in one scenario, I can create definite kicks because of absorption. Other scenario gives me random. So you see that I'm able to slow down a definite direction of the input velocity. Okay, I can slow this down. That is, if I have the, for example, if I have my atom coming in this direction and my light fields are coming from that direction, I'll be able to slow down this definite velocity. But you see that this will also lead to random motion of the atom, whereas this definite velocity in a particular direction will get slowed down because of absorption.